coming. And before I introduce our speaker today, I just want to welcome you back to our Distinguished Lecture Series and give you a heads up. 4 weeks from today, we're going to have a speaker, Nir Eyal, who wrote a book called Hooked, which some of you may be using in your class, apparently. It's all about basically the hooks, how to engage a user of an app or a software program. So he's going to be, this is going to be a little different next time. We're going to see a video. He did like a TED Talk. And then he's going to be live online to answer our questions. So you have to, if you want to watch the video ahead of time, you can Google him, and then you can think of some amazing questions. So we'll have him piped in. So that's 4 weeks from today. But not to distract from today's speaker, who is just an amazing person. We just came back from lunch, and Yvonne Cagle is a person of many accomplishments, as you will discover during this hour. She has a whole bunch of degrees, bachelor's degree in biochemistry, a medical doctor degree. She was a practicing doctor for 15 years. Then she decided, well, no, she really wanted to be an astronaut. She went off and signed up, did astronaut training, and she has a list of awards as long as your arm. I will just outstanding young woman of the year of America, National Defense Service Medal, Air Force Achievement Medal, U.S. Air Force Air Staff Exceptional Physician Commendation, National Technical Association Distinguished Scientist Award, and I'm going to stop. There's more. I won't even go through them there. But she was an Air Force colonel when she retired from the Air Force. So all these paths, and I think you'll see it's very inspiring. I did a little other research and found that she, for example, something local to here, designed a 3D printed buckle for exercise in space, made by Made in Space, which was started, just one building over. Made in Space, it was a zero gravity printer, 3D printer, which I think they've exited from next door now. I think they're bigger now. They're going to San Francisco or something. But or space, right? Yeah, but it's on the space station now, I believe, that printer. So, and hers is going to be, I think, was the first thing that was commercially printed item. Right, was the buckle she designed. So there you go. And over lunch, we probed for a few more sort of human stories of her background. So I'm going to tell you 3 different things about her. So one is her background Air Force, NASA and stuff. So she spent some time in Texas. So one of the unusual things you may not know is she had the experience of walking half a dozen armadillos on a leash, just like a dog, And one, she actually experienced a garden party where she attended the garden party for 2 hours wearing stiletto heels, thereby aerating the lawn. When she was telling this story, I thought she said aerating the lawn, as in like strafing it or something. But no, aerating, with the heels. And a third story was she would go skate in a public park in a major city with roller skating while juggling, while carrying a boombox and wearing a bright orange sweater. Now, she's good. They were there in case I forgot some of the details. Now, here's a challenge for you guys. 2 of those are true, and 1 of them is made up. So, a little quiz now. Think back about those 3 things, okay? Juggling and boomboxing, or armadillos, or garden party aerating the lawn. I want to hear a vote of who, we're going to vote on which one we think is false. Okay, so who thinks?
Before you do that,
okay.
When we did this before at lunch, it didn't sound that bad, but now hearing that 2 of them are true, I am a little concerned about myself now.
That's
one
right.
Any is bad enough. One,
that's,
you should have done it the other way.
Well,
right,
there you go. So 2 of them are crazy things, but they're all 3 crazy things. One of them is not true. So who votes for the false one being the armadillos? 1, 2, 3, 4, 5. Okay. Who votes for the garden party being the false one? Ooh, popular. 1, 2, 3, 4, 5, 6, 7, 8, 9. And who votes for the juggling, boombox, roller skating one? Okay, 1, 2. So the winner on the false one, well, the most voted on the false one was the garden party.
Because they don't buy the stiletto.
They don't buy the stiletto
I told
heel.
you I would end up depressed.
But she did do that.
Oh, we did.
She did that, and she did the juggling and the boombox as well. She did not watch Armadillos in Texas, but there you go. Anyway, I've used up way too much time.
No, this is fun.
We're going to now hear this amazing story from Yvonne.
Gosh. If we have time, I'll tell you the armadillo. There is an armadillo story, though, but I wouldn't have been walking. I was actually running from them. But in any event, all right. So in this lab, you will learn about the design and the last data hand. Oh, no, that's not me. Okay, so anyway, it was actually here. I was like, wow, notes. Hi, I'm Dr. Yvonne Cagle, and I should do a shout out to Fordham University since I'm detailed there currently for my current technical job with NASA. I'm doing behavior performance seminars for long duration space crews. And they were kind enough to award me with an honorary PhD in human health and science for your lifetime contributions. And as some comedian or someone said, when they give you a lifetime, that tells you you've been around way too long and it's time for Elvis to leave the building. So, but no, in all, Fordham University, yeah, thank you very much. So what I wanted to do is talk to you a little bit about my journey and some of my reflections and insights and innovations. And to get started, I already, we don't call it fail anymore. We call it not this time. I already did the night. Can you all hear me? I don't see the green light, but they. Oh, I guess they have to hear me because if you're recording it, you want to pick it up. Oh, right, exactly.
Well, the microphone on the podium is on, so in the meantime.
Okay, well, I'll just kind of lean, lean forward, lean to the side.
It's good. He says it's good.
Oh, great. Okay. You know, if I always like to start out with something kind of low key and relaxing and quiet. So 17,500 miles per hour, 7.5 million pounds of thrust, where the vibration under your seat is so great that you never actually see a space shuttle launch. You actually feel it. You experience it. So how do you get to 17,500 miles per hour and 7.5 million pounds of thrust? Well, it all starts at the top of an old oak tree. One hot summer night, July 1969. And you also need an epic game of hide-and-go-seek going on. So we had all the neighborhoods together. It must have been like 300 kids, or it seemed like it. And we're running the streets for like hours. And everybody is looking east and west. And they found everyone, or everyone's, you know, turned themselves in or whatever. East and west, east and west. But nobody after 3 hours has found me. They're all still looking for me. And I'm sure they thought I was abducted or abduction or something along those lines, because everyone's looking east and west. No one was looking north or south. Because if they had looked north, that's where I was hiding, at the top of this old oak tree. And the way that I was passing the time was just kind of kick back, counting the stars, and talking to the man on the moon. When suddenly, out of the darkness, I hear this voice calling my name, Yvonne, Yvonne, Yvonne. And I'm like convinced it's got to be destiny has finally found me. This is my moment. I'm ready to take that next giant leap, which probably wasn't a wise thing to do at the top of a very old oak tree. But just before I did, I recognized this had a familiar ring to it, that voice, and suddenly realized it was my dad calling me to come down from the tree and to come inside. You know, parents, I was going for the Guinness Book of World Records. If you look in the Book of World, you won't see me, only because of my dad. And so you understand why I went in very sullen, thinking, this is it. I'm not listening to my parents anymore. This is better be good. And it was great, because they pointed to the TV and there was this old grainy image of a man walking on the moon. Oh my gosh, July 1969. I had just been talking to him. At that moment, well, the first thing I did was to run back out to see if I could see him. And guess what I saw? Nothing. Come on. Yeah, right. Yeah. So I figured, you know, like you, I had missed him. Run back in. Still, there's a man walking on the moon on TV. And I'm like, I didn't miss him. You know, I run back out there and I looked, and guess what I saw? Nothing. Okay, I ran back in, literally still there, ran back out. And I'm like, guess what? I thought, people, we can do this all day. It just is never going to, didn't see anything. But the only thing that was more amazing than man walking on the moon was, or me, being able to see it, was what I must look like to that man. Granted, a crazy 12-year-old running in and out, like walking, on Earth. And suddenly I too wanted to have that view. I too wanted to one day see my footprint on the moon. At that moment, my dreams took wings, and I never looked back. So my next challenge was, now how do I get to the moon? How do I get into space? Well, I just graduated not too long ago from tricycles, and that just wasn't quite going to do it. So then I really was interested in medicine and thought, wow, prosthetics, because the human body just isn't going to do it. We need to do something kind of prosthetic, robotic, oriented. But figured even that doesn't go fast enough. We still have to break Earth's gravity. And of course, by then we had Star Trek and many of these other things. So I'm thinking spaceship. We need something really powered. Well, fast forward onto San Francisco State University, earned my undergraduate in biochemistry, onto the University of Washington School of Medicine on an Air Force scholarship. And after 22 years, rising to the rank of full bird colonel and yanking and banking in a wide variety of high performance jets, taking care of the pilots as their kind of team doctor and the crew. So I meant F-111s, F-15s, F-16s, F-18s, helicopters, heavies, air-to-air refuelers, you name it, anything going to altitude, I wanted to be in it. Yet after a while, I began to realize that those jets didn't go quite fast enough, nor quite high enough. And that's when I realized the only way to go was up, and the only way to get there was, at that time, the space shuttle. And the space shuttle, oh my gosh. If I could put poetry to motion, I would call it the space shuttle with its transportation system. I mean, in less than 10 minutes, you're 250 miles above the Earth, going 17,500 miles per hour on your way to Mach 25. And as you unbuckle your seatbelt, you're floating. And this is what I get to do. I get to train for that floating experience so that you can actually look out the window and find that your first word out of your mouth is, whoa. But very shortly after that, the second word out of your mouth is, whoa. So that's what it's all about. And so much of my training I've spent floating, learning about how the human body behaves in space and how you do science and engineering in weightlessness in a gravity eliminated environment. So let's talk a little bit about space. This is the fun thing, because I want to talk about what we've done, where we're going, and how we're going to get there. So some examples of what we've done. Well, we've left the planet, orbited the Earth. We've actually gone on to the moon. And we have basically a probe that's been to every planet that was known at that time. So it started out 9 planets. And then we went, oops, sorry, Pluto, but you can't just do that. I mean, how do you say we made it? That's an error. That is kind of a fail. I'm sorry. It is not yet. That is, you don't go after all this time. But then they kind of corrected and said, okay, we're going to make you a dwarf planet, kind of back in. And then, oh, by the way, I'm sorry, Kepler mission, there's actually 2,300 planets, a little bit off there. On our way to 2,500, 250 that are like Earth-like, which is really cool because that's where we're going to be aiming for, looking for life. There's a very good chance that if we find something Earth-like and there's water, then you're very close to the components of life. So that's why we're excited about those particular planets. We found water, water ice, water on the moon, water ice on Mars. Let's see, what have we done? I talked about Kepler, finding all those extra planets there. It's nice to have choices, I always say. The Hubble telescope that has imaged our galaxies to show that we are not alone. There are so many that actually our galaxy, if you go to, I guess it's, gosh, got to get this right. It was just there. Anyway, if you go to one of our research centers, is this? Goddard? Goddard, yeah, maybe Goddard. But anyway, where Hubble telescope is, I know this. I was just there on a plane and everything. In any event, they've got this beautiful picture, and it shows all these galaxies that Hubble has taken images of. And you look, and somewhere in there, there's like 3 tiny red dots, and that's Earth. That's our galaxy. And there's actually all of this around us. It's absolutely amazing. What's more amazing is, well, let's keep talking about what we've done. So that's what we've done so far. And we have the solar sail. You may know about that. And this is looking to accelerate the movement of particles and spacecraft potentially across vast distances, astronomical units, like the distance from the Earth to the Sun, which is like something around 150 million miles. It's accelerating things, and that's the solar sail using solar wind, so radiation hitting an actual sail and just going. So that's really great. These are examples of things that we've done. Where are we going? Okay, so where we're going is, remember that Hubble telescope? Well, now it's the James Webb telescope. And that is this gold-plated, huge lens that's going to be able to image even more. We are certainly going not just back to the moon, but we're going to the dark side of the moon. What is on the other side of the moon? I mean, we've already studied the atmosphere and the dust. I shouldn't say atmosphere, but lunar atmosphere and the dust that the Apollo astronauts encountered. But now we get to really do more analysis of it. We're looking for life in the water that we found. Of course, we're going to Mars 2030. We're still looking at boots on the ground with precursor robotic missions. That solar sail I talked about is now an e-sail. They're using photon power, beam power, to use photons that are just one of the photon wires is like half the size of a hair. And the whole probe itself is actually about 5 hairs. And it's going to be accelerated. And it can go so fast, is what they're looking at, as early as 2025, that it can go that distance that, let me think, Voyager 1 probe, okay? It's been 134 astronomical units, so 158 million miles, 134 times over 40 years. So this will be able to do it in 5 years. So it's about somewhere an eighth, and probably by the time it gets going, 1/10 of the time to get there. So instead of months, it'll take weeks. So instead of a season or more than a season, 4 months to get from Earth to Sun that we can do now, it's going to be able to do it in less than 2 weeks. So I would save your frequent flyer miles, because you're really going to launch sometime soon. So that's kind of what we've done, where we're going. But I also want to talk also about how we brought space back down to Earth. And we've done that in a number of ways. The cell phones in your pocket, foldable batteries, solar arrays, even your children, the fire retardant pajamas that they wear, smoke detectors, your sunglasses, the lenses in your glasses, and even the de-icing on the plane that brings us to our loved ones and brings us back home again. Although why you and your loved ones aren't in the same place, I don't know. But as an astronaut, that's usually how it works. So there's so many things we can look around where we have brought space back down to Earth, and we continue to do so. We see it in our medical equipment and our medical devices, and we're helping out with ways to really move that forward. So it's not only in the mammograms that image and other things. We're using some of the Hubble technology. I shouldn't say Hubble tech. It's called InnerView, and it's able to use some of the Kepler technology for your arthroscopic or knee surgeries. So now there's minimal bleeding, minimal disruption. You don't need the same amount of anesthesia or sedation, and you can oftentimes go home in the same day. So it can do diagnostics and image for the surgery. Healing is very fast now that we don't have to be so disruptive. We also have a NASA biocapsule, and it's inert. It's the size of your thumbnail, and it can actually go inside you and not only diagnose infections and illnesses and metabolic disturbances like diabetes and some cancers, but it can also treat it real time, be its own delivery system. And that's all with this particular capsule. We're working with people on the tricorder so that we don't have to carry stethoscopes and ECG, EKG machines and thermometers and blood pressure cuffs and pulse oxes, but we can bundle them all on a single smartphone platform so that you can even have it at home for your own personal health care and monitoring, and be your own kind of point of care and transmit that information to your doctor and hospitals without leaving the comfort of your own home. So that's just some of the examples. And then let's see if we get to the one that, so many things we're doing where we're changing lives in terms of genetic sequencing, genome sequencing, nutrition, all of these things that we're learning for space and long duration crew have many applications right back here on Earth. I love Smithsonian Rex. People look at this and they go, oh, we're going to be turning people into robots and cyborgs and everything. Actually, Smithsonian Rex is a laboratory for health. Every organ practically on Smithsonian Rex is something that can serve as a simulation and demonstration platform to refine the things that we need to improve the organs that are failing or are having issues. And so once we demonstrate how to do it well, there's a much higher opportunity to have it improve the lives of our parents, grandparents, ourselves after trauma, injury, illness, those sorts of things. Smithsonian Rex, you can take a look. He's got synthetic skin. He's got hearing implants. He's got so the cochlear implants, the eyes. He's got retinal implants, heart and lungs, spleen, kidneys are all working organ systems. The hands and the limbs have almost as many degrees of rotation and movement as a human does, and the exoskeleton actually allows Smithsonian Rex to stand. So this is really a living, breathing, walking laboratory that will actually enhance our lives. And then there's lift. Lift. How many people would like to have the equivalent of both aerobic and anaerobic exercise, 2 hours worth in only 20 minutes? We're all really busy. Anybody too busy? And that could kind of, okay, great. And it's a wearable fitness accelerator that not only accelerates healing of soft tissue strains and sprains, it's been shown and demonstrated to do this, but also accelerates reconditioning if you're not injured, or to advance your or amplify your performance for those who are training in whatever kind of performance competition work environment that they want. These are things that we're all ground truthing and demonstrating and evolving. It's still in stealth mode, so if you want to know more, come see me. But where we really see it as being not just a game changer, but a life changer, which is really where our passion and our driver is with people who have had, stroke or Parkinson's, or post some kind of therapy that has left them so deconditioned and weak that they can't even hold their baby. So, where a performer might get extra muscle and change their peak performance time, real performance is life performance. And so when you can push a wheelchair or stand in an exoskeleton or hold your child, to me, that's where the real game-changing, life-transforming impact is. So that's lift. Yes, please definitely see me afterwards and we can talk more. There's lots of opportunities there. So I've talked about what we've done, where we've been, and now let's talk about how we're going to get there. The way that we're going to get there is by exercising the muscle between our ears. Speaking of ears, we're talking about the space between our ears, which is basically our brains. That's how we're going to get there. And it's not even me. I'm really focusing on the next generation, because that's the galaxy picture that I was talking about. And somewhere in there, there's 3 tiny red dots that constitute our Earth, Moon, and Sun. So this is what lies between your ears. How we're getting there is the next generation. And how we're going to do that, you're already doing it today. I don't have the answer. You have the answer, and you're performing it as we speak. One example is Autodesk. The Autodesk designed for industry challenges. And that's where Autodesk is collaborating and partnering with industry in order to mentor and give firsthand hands-on experience for young people, next geners 18 to 24, to team together, and I love team because that's what I call STEAM, teams, is technology, engineering, art, math, and science. So to team together to solve these design for industry challenges. And the first challenge that went out, the deadline closed, I guess, August 31st, but I was a judge for was the Design for Space Challenge. And basically what they had to do was 18 to 24-year-olds from 70 countries. We started out with 6 entries, and we closed with 3,200 entries. And 70 countries participated, and they had to design a CubeSat that would be able to take a decommissioned satellite from LEO, low Earth orbit, to station keeping in GEO. And basically, the challenge that I helped to kind of write was that our big concern is access to space. You know, it seems like there's a lot of space out there. There's not. There's only certain trajectories and corridors. Ask Katherine Johnson, see the movie Hidden Figures, the mathematician woman who calculated the launch window and trajectory to not only get man off planet, but landed man on the moon, humans, I should say. Just happened to be man anyway. This time around, Mars, look out. And actually got our Apollo 13 crew back home safely, which is a challenge because the mold was broken on that one, didn't know how to do it. A woman and her team and women like her. The only reason we're counting down today is because Katherine Johnson and women like her were counting up. They calculated computers who wore skirts and did it while carrying and working off of a slide ruler. That's like me and stilettos at a garden party. It just doesn't connect. It doesn't compute, but she did it. And it's an amazing story. So I really encourage you to read all about her. But it was because of that that we now have access to space. So the last thing we want to do is to close all of that down. And there's only, as Katherine Johnson will tell you, there's only certain corridors that you can actually hit in order to nail just the right landing. And there's about 3 things that you have to get perfectly right or nothing works. Same thing with lift. There's three requirements that if you don't get right, then it doesn't work at all. So she had that challenge. We want to keep that open because if we close off any of those corridors to space by clogging the lanes up with space debris or satellites, swarm satellites, great idea. But if we clog it all up, now we have space debris and it becomes not a space voyage or expedition, it becomes space dodgeball. So for those of you who saw Spaceballs, this is kind of with the dodge. Literally, we'll be dodging things that could puncture the spacecraft or the suit. So we have to be very responsible about it. And space debris is not space trash. It could be space salvage, where you collect it and bring it back to some salvage yard to be able to use as a way station should you need it. People say just explode it and break it up. You don't want to do that because now instead of 1 piece of debris, you've got, you know, 1 million more pieces. And there's a station in Colorado that tracks every piece of space debris. And it's a small station in Colorado, and these young people do amazing jobs. But, you know, come on, cut them some slack. Let's not just really make them stay up all night. So that's what the challenge was. And so they had to design a CubeSat. And it had to have, so for access to space, it had to have battery power. It had to have communication system. It had to have a docking and grappling system and the cameras to help with it. It had to have flight control capability. It had to have, of course, the software and the coding that goes with it. It had to have thrusters and solar arrays. And these are just some of the things that were in the requirements. And then it had to be able to get the job done. And they had to account for all of these things. So what I'd like to do is to show you what the winners look like. And let's see if I can do this. All right, so here we go. You know, I'm thinking about the shoebox, the bread box. This is the designs. And I'm just going to scroll because I certainly don't want to give away the details. You can look on the Autodesk site and find out more about it. and there's many other opportunities to further evolve their prototypes as we go. But you see the variety of shapes and designs and engineering, and that's what the challenge is all about, bringing together designers, engineers, and architects to come up with these solutions. And these were like mind-blowing. So there's other industry challenges that are coming up, and if you're interested, certainly feel free to check it out. So that's one example of how we're going to get there. The other example is something called, I don't know if you've heard this place, it's called CMU, Carnegie Mellon. You have a long, rich history of collaboration with NASA. And it's a very short roll call, but if you don't know, I'm just going to name a few things, but there are so many others that you could probably chime in and add to the list. But certainly you're leading the way in our collaboration in terms of robotics and rovers and working out robotic language. Your intelligent systems, intelligent design systems with your machine learning and adaptive controls. You've got your unmanned aerial systems that are using magnetic monitoring to look at the geophysical characteristics of the subsurface of the Earth that can serve as an early detection for earthquakes and other extreme weather. You've also got, I like this one, genetic algorithms, which is actually an antenna that goes with the IRIS mission that is looking at the subsurface, the low atmosphere, the lower atmosphere of the sun, and looking at the movement of energy and particles, imaging that movement of solar energy and particles between the subsurface of the sun and its corona itself. There are emergency operations center that NASA has in collaboration with a number of people in industry, but looking at the wildfire research and applications, that certainly has great relevance here. And also, I love it, the Neuro networks that are forecasting solar power for sustainability base, our sustainability building right across the street. So you all really bring it home and take it off the planet. And I just want you all to give yourselves a pat on the back, a round of applause, because we really can't do it without you. So in closing, with all of that said, I could summarize everything that I've been, saying in 3 words, and that is possibility is endless, and it's only limited by your ability to dream the impossible, because not even the impossible is impossible. Because if we decode the word impossible, there are only 2 letters standing in the way of you and what's possible. And those letters are the letter I and the letter M. And if you say it together with me, what do you get? You get I am possible. I am possible. So nothing is impossible, and there's space for all. Thank you. So if we still have time, I'm happy to take a few questions. Great. I forgot to say, put your seatbelt on. And please, somebody ask the armadillo question.
So in regard to the future Mars missions, from a medical point of view, what do you think are the challenges and how are we going to solve them?
Wow, that's great from a medical point of view. Well, you're right. We can get to Mars. The rate limiter is really the human body. We're going to figure out the propulsion and how to do our insertion through Mars's gravity and land and everything. We can do that. We can do it robotically today even. The challenge is, how do we bring humans along with it? Humans are the rate limiter. So robotic precursor missions to kind of do the survey and give us information and data. Sorry, that's Florence now. No, you can't. No, you can't. I always forget to do this. No, NASA, we don't have. No, Houston, we're good. No, yeah. So I know they solve problems, but we don't have a problem for them to solve. Okay, all right. Well, I'll be sure. We'll come up with a bunch of problems for them to solve. Okay, great. Thanks. Don't call me again. Yeah, at least not for another few minutes. Yeah. But call me definitely. Yeah. Right, definitely. Yeah. Right. Anytime. Right. Yeah. Great. Thanks. All right. Bye. Anyway, sorry about that. My apologies. Okay. Don't worry. Sometimes I talk to aliens, armadillos. It doesn't matter. The unusual for anyone else. So the humans are the rate limiters, and it's number one is radiation. How are we going to deal with radiation? And I mean, the deeper you go into space, even moon, there's so much radiation that can cause reactivation of infections, and it can cause cancers and infertility and many other things. So what we do right now is we try to shield the vehicle. And water's the best shielder. You can use plastics. You can use different carbonate type materials. But all of them have a certain cost or up mass that we haven't really reconciled yet. We have kind of weather radiation shelters that we can get into, radiation bags that we can use to shelter if there's a solar flare. They give the colony enough time, we might even be able to move the entire station, which is typically what we do when we have enough warning. But interestingly enough, at the end of the day, even with the shielding is almost its own liability, because now when it hits the shield, instead of being protected, it's sort of like the space debris. Instead of one hit, now you've got this wave effect. It's broken up, and it actually slows it down so it stays in your body longer doing damage. So you're better having it just sort of just go screaming through, let it take out, your immune system or whatever it wants to do, and then have, we can 3D print tissue and 3D print your bone marrow if we baseline that before you go. Then after the storm is over, re-inject it. We all kind of stay kind of in our isolation areas for several days or weeks until we reharvest and regrow and reimplant that marrow, and then come out and go again. So it's better to take a through and through than to take a little bit that kind of stays. So that's the radiation side of it. The bones demineralize like osteoporosis, and muscles actually atrophy. Osteoporosis, we lose about 1% of our bone a month. It plateaus for some reason at 17%, but that's only in low Earth orbit. We don't know if it kicks on and there continues to be loss if you continue to go longer in microgravity. Muscles you lose at the end of a mission, somewhere around about 10% of your muscle mass, but your strength is even more. And those of you who saw Matt Damon in March, and at the end you saw how he's malnourished and undernourished, and his skin and everything like that. We got to find a way to keep folks fit when they don't have resistance to work again. That gets back to, I won't go into, didn't say anything, but just remember stealth mode. So we're working that, and we're trying to ground truth that, and there may not be a there, but we're really excited about what we think we're seeing. More on that later if you're interested. So we think we've got that, but the bigger challenge, and then there's other things that happen. Your exercise tolerance goes down as your heart deconditions. But the good news is, good news is great, expedition, exploration, and it's only really an issue if you want to come back to a gravity environment. So as long as you want to go on my crew, one way, Mars, not coming back, colonizers, we're good. We're primed for space, all right? But if you're going to space and you look around and you see me on the crew, or it's probably not it's not coming back again. So just sort of do a head count before. So that's a problem with humans, and there's other systems that get disturbed as well as your neurocognitive. And at Fordham University, looking at behavioral performance, we're actually not only solving the biggest challenge of humans at space, which is that behavioral sensory deprivation, isolation, communication, how that manifests on your crew interactions, but we're tracking it all the way back to early warning signs that we believe we can identify neurocognitively with neurocognitive testing and data. And it can even point to functional areas of the brain that we potentially can, fMRI image and be able to see that there's disturbances happening before you even get behavioral signs. And we can start identifying and training and coaching and conditioning it so that we never have to actually do a course correction. So that's kind of the human situation. We've got a lot of work to do on that. We just took Scott Kelly back off after almost a year in space. We're learning a lot. So we're still on track for 2030, but our work is definitely cut out for us. Wow. Now that I've answered all the questions, though. And while you're thinking armadillo, you want the armadillo story? Okay.
So what about all the astronaut training? What did you find the hardest part?
The hardest part of astronaut training, the hardest part for me, it's funny, the best astronauts, because it's all upper body, basically your legs are redundant, if anything, and not even redundant. There's when you're floating and everything, so it's all upper body. So the best astronauts are probably those who are paraplegic and have incredible upper body strength and have learned to navigate here on Earth. They already have the strategies to be in space and everything, so that's great. And then the other group, and that's why I always put the prosthetic picture in the talk. The other group are actually kids, because they can get on those merry-go-rounds and just like, have you ever had a kid spin you on a merry-go-round? You're like, oh, I want that little girl there to go ahead and spin me, and you climb on, you think it's going to be a 5-year-old, and I see, no, they just like, because that's what they're used to. Never have an old person spin you, because one, they're not going to have the strength, and two, they're going to go easy. The kids get on those things, and I watch them at the playground, and they just spin, 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 and so they're the ones who can really adapt to this disoriented, changing orientation. And also because they are the vessel of artificial gravity. And again, for proprietary reasons, I can't go into it. But basically, they're training in artificial gravity. I can say it's similar to the human-powered centrifuge that NASA has, where we're using centrifugal acceleration to help recondition the body so that you don't get orthostatically intolerant. But there's even more value to the physics behind that. And again, see me afterwards. Yeah. So for me, the most difficult part was actually weightlessness. You know, the picture that you saw, 0G, because after you get selected, you do this fan flight. The first time you're going to be weightless since you were in the womb, right? So the night before, you're all excited and everything like that. And you get on and you're going, you know, you got to go to flight level 250 and you get up there and you're all set. They give you the over-the-top call, which means that, you know, you're about to do this dive, this 30-second dive, and everything goes weightless and everything floats. And you're just like, this is great. You get the over-the-top call and you're already, all of a sudden it hits you. Wait a minute. Well, it should be, and it did for some people. Those people who go nowadays before we do the dip, though, usually it's but many after the dip. It's the most fun you'll ever have growing up. And you can't condition, you know, merry-go-rounds, roller coasters. They're not, nothing's predictive. The rotating chair, they finally got rid of that because it's not predictive. But it's more like the boat, the floating on the ocean. That slow resonance is the so you're all set. You get the call. You're ready to go, and everything like that. And all of a sudden, random thoughts come into your head, and it goes, what happens? That's why it's not good. All the folks in the room here, your mind's at, you think too much, you know too much. Because you do the what happens. You go, all set. Couldn't just leave it alone. Couldn't just go over the top and float and call it a day. No, you have to go, what happens? See, it's always that what happens. You know, what is that? Mother of invention, but also it has its own issues. So what happens if we go up and over the top and everything around me starts to float? Everybody, everything. It's the law of the physics. Everything floats except for me. What if I don't? What if I don't float? And it's not even the not floating. I mean, that's hard enough, but everyone's going to see you're not floating, and I have no explanation. What do you say? So I'm like 6 seconds away, and I'm just going, I know I'm not going to float. I'm not going to float, you know, imposter syndrome. No, for some reason, I will be the first. I'm not going to float. And I'm thinking, I got to come up with something. So about 0.6 seconds before it actually happens, I go, I know. See, I was stationed in England, so I know all about roundabouts. And the cool thing about the roundabouts is, remember, I know north-south, I don't know east-west. So when I get a roundabout, I go around and around and around. And I used to just be like, oh, this is so embarrassing, until I realized that anybody who really knows where they're going has already taken their exit, and they're not going to see me going around, right? Only the people who are as lost as I am are going to know that I'm going around, right? So I have to recreate the roundabout in about 0.4 seconds now. I'm thinking, I'm going, oh, I know. If I start jumping at just the right frequency, I'll look like I'm floating, because everybody will kind of be doing the look and everything like that. And, you know, so that's what I was prepared to do. I'm all set. And sure enough, we get over the top. Everything around me starts to float. I'm just what I'm going, see, I knew it. And I'm ready to start jumping. And then suddenly, okay, I start to float too. So that was the scariest thing right there. I was like just sheer terror. Anything after that was, yeah. So something to think about, because there's never say never. It might be you one day. Just I want you to think about that just before. But yeah, it's a great time if you've ever experienced weightlessness. And we test things out on the KC Vomit Comet, the 135. So if you're doing some kind of experiment and you want to check it out, that's definitely the way to go.
We have a question coming in from Pittsburgh.
Oh.
Where do you see the application of current popular computer science trends like data science, application, artificial intelligence, cybersecurity, etc., in space?
Wow. All right. Wow. All right. Give me the list again. All the things that they.
Where do you see these various computer science trends? Data science, like big data.
Big data, right.
Artificial intelligence, cybersecurity.
Wow. Wow. Those are all really great questions. They all come down to being able to collect data, crunch big data, and being able to have some sort of machine learning that you can put into adaptive systems. So I don't have specific answers for any of those, but what I can say is that CMU already is working the tools for all of those. So you all are actually setting on the answers for that, and I'll be really excited for it to go. Just to touch on some of it though, big data, you know, we've talked with Google and others about how you take all of this galactic, cosmic, solar data. There's just so much of it. And the challenge we used to say was collecting the data. That's not the big thing now. The big thing really is calculating, is being able to analyze it, being able to compress and crunch it. And that's why, you know, we can't do it with all that of our neural capacity right now. It's really going to take some kind of artificial intelligence and machine learning. But even that can't keep up with it. You know, the computing power in our cell phones right now, basically we've got more than we had when we got the shuttle off of the planet, when we got man off of the planet. Just think, we had a slide rule and limited computing power. If anything, it's actually the women who wore skirts and did the computing. And now we've come all the way this way. So the problem is we've got all of this data. How do we actually handle big data? And then when we have it, it's like all the wearable fitness things that you have now. We've got all this data, but what is actionable? And that's the big thing. And they're finding that there's even limitations to robotic and machine learning, to the point where we may have to hijack the human brain neurons and find out how to hack the brain's neuronal chip in order to somehow use that as its processing center. Now that sounds really bizarre and strange. It's actually already being done. There's already a startup that's doing it. So they're driving the brain's neuron in order to be able to. So that tells us we're not totally all Smithsonian Rex. Let's not give it away, because Rex may need us. And then in terms of security, is it security general or cybersecurity? Cybersecurity. Yeah. Those are the challenges that are actually limiting us being able to move forward with medical technology because of the hackability of data and our privacy. And it's going to be as great a challenge in space, because the best thing about space is there's nothing like it on Earth, including no borders to separate us. The worst thing about it is because that means that there's a lot of patency and exposure in a cyber way. So those are in part technical solutions, but there are also a lot of ethical and legal. So as you innovate and design, think about what the ramifications and implications are. We have to learn how to hide data in plain sight. And that's only part of it. The other part is just being, responsible neighbors for each other and our environment.
We have other questions. One other from Pittsburgh. Go ahead.
So, in terms of human spaceflight, what do you think will be the greatest impact of the private industry? Companies like SpaceX or Bigelow, Blue Origin. What do you think they're gonna make the biggest impact?
That's Bigelow now. Just, I got this. No. Just, he's asking me. Stop. It'll stop. Don't worry. Yeah, no. So yeah, the biggest impact in terms of medical hearing. I think the biggest impact is really exciting. It's not something that people think about, but in terms of medical and humans in space, the more we can start to decode how the human body adapts in altered gravity environment, that's only half of the excitement. The other half is now, once we understand it, how can we manipulate it? How can we drive it? And how can we target it, again, responsibly to help for conditions here on Earth? Because many medical conditions are just normal conditions that have sort of gone into a different environment. I don't want to say that cancer is good or infection is our friend, but if you think of it as just a different environment that the human physiology has to perform to, then we can manipulate that environment and find ways to come up with cures and interventions. So for me, I think that we're going to find a lot of analogs and conditions that simulate illnesses that we have on Earth. And as we learn to solve them in space and in these different environments, muscle and bone and mind, it again tracks to osteoporosis and congestive heart failure and neurodegenerative and Alzheimer's and Parkinson's and all of these things. We may find ways that the human body has more potential and capacity than we've given it credit for. And that's what we're starting to see with things like lift and its stealth mode and everything like that, is they're starting to find pathways that can be reprogrammed. So we already know that the brain is plastic, has plastic in terms of plasticity, neuroplasticity, meaning that it can adapt. And that's really wonderful. And I remember when I first started talking about plasticity and neuroplasticity long before it was the thing, and people thought I was out of my mind, no pun intended. And now it's the big thing. But now I'm talking to the next level of, bizarro, which is, I think there's physioplasticity. I think metabolically and physiologically, we can also influence intrinsically how our body performs in order to enhance our performance. I should say amplify our performance or accelerate our recovery. But I'm already 2 steps ahead in the sort of off-the-planet thinking, is because of what we're seeing at Fordham and behavioral changes and how it tracks to parts of the brain, especially I'm trying to think how much of that is proprietary, but there's an area that we believe is the most fragile area, and we're targeting, and it tracks to some of the conditions that we see with learning disorders and traumatic brain injury and concussion. And we have many analog environments for that, from football players all the way to children with autism or attention deficit and everything in between. So we can practice and use some of these coachable lessons. So we know that there's plasticity, we know that there's adaptability, but the next region, and this is what we're seeing with our performance studies, is that it looks like there may even be neuro remodeling. In other words, things don't just adapt and then change back when you go off planet and then come back to gravity, but it may actually remodel so that you go to space, but when you come back, your parts of your brain or body may still be in kind of a space mode. It's actually remodeled. And so suddenly Earth becomes, I don't want to say the illness, but you're not adapting to Earth, and space is your normal. So if you look at that for illness too, then it's really all in context. We can just make the environment support and be habitable for the adaptation that we want. Even with the remodeling, there are ways to potentially change it back, and we have ideas about it's really reconstructing that environment and giving either hyper-stress exposure or low titrated aliquots until you can get back to that sort of readaptation. But remodeling is really interesting because if we know that the brain can remodel based on environmental factors, then can we remodel the brain in terms of our own sort of anti-machine learning? In other words, somebody who's had a stroke all the way to somebody who has a learning condition, can we find ways to amplify and improve that too? Long answer just to say that I think space is really a demonstration platform. It's not just a destination. It's really a demonstration platform that we can learn from and then make sure that we bring those applications back here to Earth.
Since we're running out of time and since no one has asked, I'd like to know what you think about intelligent life.
That is great. I love that question. Oh my gosh. You must have been reading my mind. Hey. Yes, it's funny. You corralled me because you said intelligent life. So now I'm like, definitely if you just do the math and that galaxy picture and everything, the fact, for us to be the only intelligent life, and for some of us not in this room, but we may know that might be a stretch or an oxymoron. But anyway, for there to be life and intelligent life at that out there, for us to be the only ones is really talking about a stretch of the imagination. There are definitely other forms of life. It's not a question, are we going in search of, or is there? It's yes to both. Yes, there is, and yes, we're going in search of. It's just the odds. It's just the math. And the universe is on the verge of being able to do it. And if it's already done it, it may just be that the life is so intelligent that either we're not on its radar or it's just choosing to be very quiet and not get found out. Exactly, that's right. And that's why accelerating and moving things, who knows what we'll be able to find. But there are definitely life forms. So one of the games that I play in my mind when I can't sleep is what would life look like? And it's going to have to be some sort of very simple, robust life form. So it may not be as evolved. We're our own liability because we've got too many moving parts. We're too complex. So something that's going to survive out there in the radiation-hardened environment of cold, dry, and dehydrated space is going to be some kind of most likely single-cell organism or an organism with some kind of fossilized form, which we've seen imprints on in different planetary investigations. So that's one thing. We've also taken tardigrades, which are water bears. We call them affectionately space bears. They look like gummy bears. And we've taken them into space. And we just took them along for the ride just to see what they do. They kind of live in swamps in and around, and they're just these adorable little, very socialized beings and everything. So we let them fly with us because we want you to be socialized, even if you are an organism. So we flew them in space, and then we put them out on our back porch. You never want to be invited to the back porch out in space because it's actually where it's very cold and very dry. It's space and radiation and everything. So they kind of did their time out there, and they dehydrated, they decompressed, they kind of died, I guess, it looked. So we brought them back in, warmed them up pro forma, just to be able to say, okay, well, they lasted or didn't last so long. But we found that as they warmed up, that they were able to get warm, rehydrate, start moving around, and actually even start procreating. Whoa. I used to think it was going to be some strong insect form, centipede type thing, or a single-celled organism, but here are tardigrades. So now we've brought them back, obviously. We want to send them again on another mission, but this time sequence their genome to find out what it is that makes them so hardened, and see again if we can drive that for human spaceflight, because whatever they have is pretty resilient. The last thing I'll say real quickly is, if you took it to what a Martian might look like, knowing its atmosphere is primarily carbon dioxide, very little oxygen, the physiologic math of it means, well, for one thing, when you go to space, you grow because the spaces between your backbones are literally space. So as you float and they separate, you get 2 inches taller. No, when you come back, if you don't colonize, you're going to shrink again. Another reason for colonization. Your waistline slims down as well. Your limbs, they thin out because they're atrophying the muscles, which makes your fingers and toes look very thin and long. Your rib cage becomes more prominent because that's kind of where things in terms of bone loss stabilize out. And your head actually increases in size because of the high, well, they don't know, but my suspicion is as plasma volume rises up, hydrostatic pressure from that plasma volume is on the skull, and it actually, hydrostatic pressure can cause new bone growth. So anyway, your head. So if you put all that together and you draw it out, which I did, guess what I drew? Who I drew? E.T. I mean, I'm looking, I'm just going, oh no, say it ain't so. So that was pretty amazing. Then all of a sudden, again, I can't go to sleep. What would happen if came into my mind. I was like, wait a minute. The only thing more bizarre than this looking like E.T. or the Sixth Sense thing or anything like that is somebody knew. Somebody got this right. How did they know? So the question is, I'm going to leave you with this, is are we going to space, or are some of us going back to space? The alien may be among us already. And when we go out there in search of the alien we find may be the one within. Time will tell.
With that, I think I would like to give you a little token of our appreciation.
Oh, cool. This is great.
You get a Carnegie Mellon backpack and
Wow.
a Carnegie Mellon mug to go
Oh,
with it.
this is awesome.
So thank you very much.
Thank you. All of you. You were great. Thank you very much.
And
So-
we got, I guess, still food outside, and
Yep,
you're
great.
sticking around for a while,
Yeah, I'm
right?
sticking around.
So
So
if you want to ask some more questions.
lift our armadillo. Let's go to the. This is
All
great.
right.
Thank you very much.